Hi everyone, I am Adrien Baudard, tunnel engineer for Bouygues Travaux Publics. I'm delighted to be having this presentation today about the semi-continuous advance for single shield machines. I think I have to start by saying that none of that would be possible without the extremely close cooperation between Herrenknecht, our tunneling boring machine supplier, and Bouygues Travaux Publics expertise in delivering ambitious tunneling projects. We are currently working in partnership with HS2, who has been extremely supportive in promoting this innovation. HS2 is Britain's new high-speed line that is being built between London and the northwest, and we'll focus today on the package C1, which was awarded back in 2017 to a line JV. The joint venture is composed of Bouygues Travaux Publics, Sir Robert McAlpine, and VolkerFitzpatrick, and is now in charge to deliver the 22-kilometer stretch between the northwest of London to the entrance of the Chiltern Hills. And there are two major assets within this package: the longest railway bridge in UK, the Colne Valley Viaduct, and a twin-bore tunnel of 10-mile long. The two TBMs are variable density machines provided by Herrenknecht. And I'm proud to say that many cutting-edge innovation have been embarked onto these machines. And I could definitely make a quick visual representation of what they are. Two robotic arms, Dobydo and Krokodyl are, for instance, working on the supply chain for the segments. One is removing the wood wedge at the back of the gantry one. The other one is installing the segment dowels before the segment is transferred onto the feeder. I could also mention the monitoring Bouygues discs, but the main one which we are going to focus on today is the continuous advance technology, which is deployed onto S1205 and S1206. And I couldn't find any better graphical representation of our problem. And I think the very question of today's presentation will be to try and understand what does it take to go from the top situation where we excavate or build sequentially to a situation where we are able to build the ring in shadow task from the advance. Essentially, that is the very ideal continuous mining. And just a teaser, unfortunately, there is still a bit of work to reach that bottom saturation. So I'll spend a bit of time explaining what challenges we have faced, what we managed to sort to develop this innovation, and where are we today? What is the state of the art? So I have to start with a bit of a boring theory. My TBM is equipped with 14 thrust cylinders. Each thrust cylinder applies a force onto the previously erected ring that allows the TBM to move forward. Each force can be depicted with a vector, and if we sum up by vector addition all of the forces, we'll have a barycentric force, which we'll call for the rest of this presentation the center of thrust. And traditionally, when the TBM operator steers the machine, effectively, he will create intentionally an eccentricity between the center of thrust and the center of gravity of the tunneling boring machine, which will tend to steer the machine in a certain direction. So for instance, in simple words, if we push more of the lower thrust cylinder pads relatively to the ones at the top, the machine will tend to go up. And then we remind ourselves of our problem for today. What does it take for me to build the ring alongside with the TBM advance? We are in an easy situation. We have 14 thrust cylinder pads. We have 7 segments. So if I want to build the rings, I will have to sequentially take off and put back on pairs of thrust cylinder pads to build the ring all around the clock and finish the ring. So if we look into that situation where, let's assume for the sake of the exercise, we are building that ring with 14 thrust cylinder pads, the very first function of the TBM is to build the tunnel where it's meant to be in its final destination. That is to say, we follow the design track alignment, we follow the SOP, or whatever other design information to confirm what direction the TBM is meant to follow, what direction the tunnel is meant. And effectively, if we think about what's happening, we want a situation where we go with 14 thrust cylinder pads while we are advancing to a situation where we have 12 thrust cylinder pads, because we still want to advance while we start erecting a ring. So assuming that very example that we've chosen our key position, we have to remove pads number 7 and 8 to allow the first segment to be placed. Just a quick note on what we said before. The center of thrust is usually below the axis because we try and find the gravity, and you will find that pads 4 to number 11 have statistically a higher pressure, a higher force than their neighbors. Coming back to my example, we want to install the first segment. We take rams 7 and rams 8 back. Sorry, we take rams 7 and rams 8 back, and we still want to follow the TBM direction as I'm still going. That means there is no other way than COT being stable necessarily means the force remains the same and the momentum remains the same. So if we take these two pads, their value drops to 0. There has to be a redistribution of force that respects this condition. Now, if we look into slightly further detail, we say the COT transit from, in this slide, the red situation to the green situation where we remove 2 pads. But what does it mean? If I remove 2 adjacent pads together, I'll have this one where I'm in the invert, the full force is applied onto these pads, and this one when the force is 0. Isn't there a risk to induce crack onto my reference ring? Isn't there a risk that this worst case scenario, only this first 2 segments are being erected? I start applying the advanced force onto them. Is that structure stable? In that temporary stage where the ring is not yet monolithic, am I able to push with the full advanced TBM force onto that unstable structure, which is not monolithic yet, with no key, no contact key? And because I'm advancing as I go, I have to start building the ring early enough into the tail scheme, which means the reference ring is also experiencing some movement while it goes through the brushes, while it's being injected. So all these questions, we had to find ourselves the answer. And the first way we could get started alongside with doing the theory was to travel back in time and go into the data of similar TBM. So we took the past few years of similar size TBM, similar size of lining, and we modelized what is the TBM behavior during excavation, what is the TBM behavior during ring build. Is this compatible to do one alongside with the other? What happens when we change the distribution on our thrust cylinder pads during advance? How does the steering happen? How does the COT moves alongside the window? Does it move a meter either side? Does it move within the size of an A4 paper? This is the question we're trying to figure out. And this was never done before. It took 2 years of research to find out. And once we have that, we have to define what is the allowable window where we want to work with 12 thrust cylinder pads, because obviously we have to start designing the TBM. We have to create dimensions. We have to find what are the worst case, what is the best case. And same on the thrust pads, and that relies more on the lining. We had to open a whole new chapter to know stability of the ring, stability of the segment, its fiber reinforced segments. What is the minimum thrust force to be safe when the segment is installed in the crown? What is the maximum thrust force I can apply to be sure that I don't create any permanent damage? And once we had that clear, we obviously had to move on to the hardware part. I know what I want on the paper. How do I make it happen on the paper? And going straight to the point, physically for the hydraulicians in the room or electromechanicians, how do you have an equipment that ensures idle hole volume displacement during ring build, as well as fine pressure control during TBM events? If you go on most of your TBMs today, when you control your POT for steering, you will actually have 2 pumps at the back, one for pressure control and one for high volume. But what if we want to do the two at the same time? How do we ensure that ambivalency of the system? So we had to go with top-of-the-height electro-hydraulic system. We had to develop a top-of-the-height cutting-edge PLC and hydraulic system that can answer the problem. We were able to look for a system to decompress the thrust cylinder pad from 300 bar to 0 in less than 3 seconds. And this was most probably our biggest technical challenge. And that took 2 years of development for the hydraulic system, 2 years of digital twin mobilization, changing all the parameters, tweaking the smallest parameter, adding some valve, adding some controls into the system to find the adequate system. But then we realized that if we want to achieve what we want, each thrust cylinders need to be piloted individually. How do you make sure that only these 2 pads come off, but the next rings, the other 2 will have to come off? So each thrust cylinder pad has to be controlled individually so that you can balance at any time, have the information of the pressure on that one pad and rebalance onto the others. So that means 14 potentiometers for your pilot. And then you expect him to control the bubble, control the fed, the conveyor, and whatever other parameters which he has to keep an eye on, alongside with him balancing the pressure in his shield of his thrust cylinder pads, because we now do the 2 concurrently. It was clear that we needed a disruptive innovation. And this is most probably the other biggest challenge that we had to face. Completely think outside the box. We don't want potentiometers anymore. It cannot work. Each thrust cylinder pad needs to be independent, 14 POTI alongside with excavation simultaneously. How do we sort out that problem? So we defined it as the human-machine interface, and the proof of concept turned out to be a touch screen, where with the tip of the finger you choose the position of the COT and the machine will steer toward the direction. And I intentionally said the machine will steer towards the direction, because that's the beauty of it now. The only input from the pilot is the advance speed and the COT. The rest during the advance, you'll have an endless feedback loop that calculates advance speed, what is the steering information, and put that back into a box that grinds all the information and gives a PLC output to adjust the pressure and to adjust the volume of oil displacement between all the thrusters. And now you understand why it's the underlying technology behind continuous advance. Because at this stage, when you have this system in place, you can now say to the PLC, I'll take pad 7 and 8 off. These pressures are going to 0. Please redistribute to the other thrust cylinder pads to keep the COT within the allowable window and within the allowable physical parameters, that is concrete limits, that is geometrical or cinematic limits. So I will use the last 2 minutes to conclude rapidly. We wanted to go from the top situation to the bottom situation. The reality is, when we do semi-continuous advance, we no longer travel at 60 millimeters a minute, but rather 45 millimeters a minute with 2 thrust cylinder pads less. That's the first drawback. Second is, we couldn't satisfy ourselves with the factor of safety with regards to the stability of 1 to 2 segment structure together at the beginning of the ring build. So we had to stop the advance, build S1 and S2, and then restart the advance and continue building the ring. So it's not the fully continuous mining as we could expect in the bottom table. It's rather a semi-continuous advance where 2 out of 7 segments are built out of the semi-continuous mining process. But with that in mind, and after more than 150 cycles of experience, we've demonstrated an average 10% productivity gain and a peak performance of 15% productivity gain. The second innovation is definitely the center of thrust touchpad. It's definitely a game changer. It considerably improves the user experience for the pilot. Any pilot on the side that you'll find will tell you how it's changed completely the piloting experience. And having said that, how could the semi-continuous advance benefit to slower TBMs where the shove is longer and when the ring build time is bigger for bigger diameter machine or harder ground conditions? HK, as expressed during BOMA, Bois Convention Center, they mentioned that a 60% productivity gain could be experienced. I cannot guarantee that, but I'm sure that we'll reach that someday. So I'll leave it with you. What could be the benefits of productivity for semi-continuous advance and the benefit for all the pilots if COT was deployed on every other machine? Thank you for your attention. It was Adrien Baudard on behalf of Bouygues Travaux Publics, and I thank you very much for your time and hope to meet you in person. Thank you.